Alright guys, we are going to talk about our weak acid titration problems, and I know that we've worked a few titration problems in class, and of course, if they're strong acid and strong base, they tend to be pretty easy. But I thought I'd work out a really detailed example of a weak acid titration so that you can see sort of the individual steps and how it changes as you go through the titration and how that will help you to graph things as you get to FRQs. So, typical sort of problem, we have a weak acid here. Okay, this is acetic acid. And we're going to titrate it with our standard solution, zero point 0.1 molar sodium hydroxide, which tends to be what we quite often use. And so we've got two basic questions here, and the titration curve is kind of the important one, but the two equations are what we need to okay, how do I, get to the titration curve? What equations do I use? And I just know that quite often that writing the equations actually tends to be the hard part for some students. So what do we need to do? What two equations do we have? Well, the obvious one is just the dissociation of the acetic acid. Okay, and so this would lead us into our standard normal everyday ice table sort of equilibrium problem where we've got our acetic acid dissociating into protons or hydrogen, technically hydronium ions, and into the acetate ion. Okay, so at the beginning of the titration, that's what we're going to work with because we've just got acid in the flask as we start the titration. And so that's what we've got is acetic acid breaking down. It's obviously not going to dissociate 100% because it's got a Ka value. It's a weak acid. So then the situation becomes, well, what do we use after that? What are the other equations that really matter to us in this? And so what happens once we start adding the sodium hydroxide, and we're not going to worry about the sodium because, again, we don't really care, right? I mean, it's going to be gone. But what's going to happen is that the hydroxide itself is going to react with the acetic acid. Okay, and so we're going to, that's a 3, sorry guys. And so what we're going to get in this case is hydroxide essentially neutralizing the acetic acid. What that's going to leave us with is acetate. Okay, again, and you'll see the similarities in these two equations, and water. Now, technically, remember that obviously water is a liquid, and these guys are aqueous, and I can't write aqueous on the board, much less on a tablet while I'm staring at the screen. Sadly, that does not look much worse than what I write it on the board, right? And so the water doesn't really matter as far as our equilibrium goes. But what this shows then is once we start adding the base, or dropping the base, one might say, cue the musical intro, once we start dropping the base in, then what happens is this neutralization occurs. And so we're going to have to work a stoichiometry problem, and then we're going to do an equilibrium problem. And what we're going to see is that we're still going to use this initial equation for the equilibrium part of things, but we're going to use this equation for the stoichiometry part of things overall. And that'll change a little bit as we go through the whole reaction, but we'll talk about that as we get there. Okay, so those two equations are what we need. So anytime you're doing one of these titration problems and the equations tend to be the hard part, you need to stop and say, okay, what's the breakdown of the thing that I have, of my titrant, okay, or I'm sorry, of my analyte, which is the thing that I'm analyzing, okay, my acetic acid. And then what happens once I add in the titrant? What happens once I add in the standardized solution? Okay, so those are the two things that we're going to work with. So the second question says to draw the titration curve. So we got a graph here, and we know that we're going to be graphing pH versus how much base do I add. And obviously we're going to start down here with 0 base, and then obviously we're going to go up. So how do we pick these numbers? Again, it doesn't really matter that much, but what you want to do is you want to make sure that you're getting past the equivalence point and that you're doing 1 or 2 points on the other side. Okay, remember that if we were going to sort of just briefly flesh out our graph, we know that, well, it's a weak acid, so I'm not going to have a pH way down here. I'm probably going to be somewhere, in the middle in the 4 range or something like that, and that it's going to slope up a little bit steeper like that. Okay, and then we're going to go like that. So we know that that's going to be the general shape of our weak acid. Equivalence point somewhere in here, going to some point up here at a high pH once we're completely in the base. Okay, so that's the general curve. But of course, we want to know what's a slightly more accurate curve. What would it actually be? And so we're going to have to do a lot of math to get that. So let's get to the math in this scenario. So we're going to look back at our original problem real quickly. and I see that I've got 50 milliliters of a 0.1 molar acetic acid, and then I've got a Ka value. And so at the beginning, when we've added 0 milliliters, that then means that essentially I've just got the acid, and so I'm just worried about that first equation. So as far as our math for 0 milliliters, I didn't actually write that down, but we'll put at 0 milliliters of sodium hydroxide, I've got a Ka value of 1.8 times 10 to the negative fifth. Never get those negatives right on here. Okay, is equal to my H plus value over my acetate value. And again, you know, since this is a weak acid, you can easily use the generalized forms. In fact, it might save you some time if you just wrote A there instead of writing acetate out every time. But that's sort of a personal thing. I know that some of you all, it becomes a little bit more difficult in your head somehow when it's generalized. Okay, so this is what we're looking for. And so if that's what I've got, if I've got that and I'm looking for my H plus so that I can calculate pH, what do I typically do? Well, I typically am going to run an ice table at that point. So let's set up our ice table. Okay, so nothing terribly complicated there. And again, if it feels like I'm going a little fast, I'm really trying not to, but I'm probably going to have to break this video up into 2 parts anyway. And so I'm trying to keep it to 2 parts and not 3 parts and still have it under 30 minutes total. Because let's be honest, you guys don't want to watch 30 minutes of me solving this problem. And of course, the problem won't take you 30 minutes to solve. I mean, it probably took me maybe 5 minutes to work out each step total. But you know, you have to be confident in what you're doing to be able to work that out pretty quickly. So our initial concentration here, remember it's an ice table, so we're talking about concentration. So my initial concentration was 0.10. I had 0 of each of these. I'm obviously going to produce, sorry, that should be X's. I'm going to produce hydrogen and the acetate, and I'm going to lose the acetic acid. And so we've got sort of a standard setup, like our very simplest. Sorry guys, it's been a long time since I wrote with the pen here on the computer, and I'm obviously bad at it right now. So this is sort of standard fare, standard setup for our normal equilibrium problems. So now we're going to substitute in here, and I'm going to put, on the top is going to be x squared, right? So we got x squared on top because both of our top values are x, both of our products. And then underneath that, we've got 0.1 minus x. And of course, then what we're going to do is we're going to look at that. We're going to say, well, since this is lower than -4, I can probably assume that away. And again, you should probably check for the 5% rule. But typically speaking, it's going to work out. I mean, we're not going to have problems on the AP exam more than likely to have any quadratics on them. So we're just going to cancel that out. We're pretty safe with that. So what we're going to do next for math is 0.1 times 1.8 times 10 to the fifth is going to be equal to x squared. So that's going to give us the next step here is going to be 1.8 times 10 to the negative sixth. I don't know why I can't do this negatives. Equals x squared. And so then we're going to take the square root, and once we take the square root, we're going to see that x is equal to 0.00134. And then, of course, we're going to plug that into our pH equation, right? So pH is the negative log of 0.00134. That's a 4, not a 9. Okay? And so once we plug that in, we're going to get our initial pH, and so that's going to be 2.87. So again, somewhere not quite at the very bottom of our pH. And so if this is 7, halfway is about 3.5. So we'll say that 3, let me make this a color that we can actually see. So we'll say that 3 is probably going to be right about there somewhere. Okay, so there's our initial pH. That gives us a starting point for our arc at least. Okay, so let's continue then to work the rest of the problems. Now, of course, that's easy. That's a regular, straight-up equilibrium problem. Nothing complicated, no common ions, no reactions really going on other than the dissociation. So what happens once we do start doing the rest of this? So I've got this set up so that you can sort of see what's going on in each step. And I'm not writing everything, first off, so that it's clear. I'll write out the math. But now you can sort of see what's going on in each piece. So once we add 10 milliliters of sodium hydroxide, what's going on? Well, remember that our sodium hydroxide is 0.1 molar. So if I'm adding 10 milliliters of it, then that means that the amount that I have then of the sodium hydroxide is 0.001 moles, or you could put 1.0 millimoles, and I know that you guys can't stand that, so I didn't put that. So 0.005 moles of acetic acid is what I had at the beginning. Again, how did I get that? 50 milliliters, 0.1 molar, we did the molarity there, and so we've got both of those things. So that's my initial situation for the stoichiometry before anything happens. So once they react, what happens? Well, obviously the hydroxide is going to be consumed, neutralizing the OH, and so I'm going to get 0 of the hydroxide left. That also means that I'm going to have 0.004 of the acetic acid left, and that means, again, if that happens, these are 1-to-1 ratios, so I'm going to get 0.001 moles of the acetate made. Okay, so that's the stoichiometry part of the equation. Again, water doesn't really matter, right? So these are what I have here now. Now, to get to equilibrium, of course, since these are moles, I need molarities, and so what I have to do to get my molarities then is that I'm going to have to divide each of these guys by the volume. And it's not by the initial volume, right? Because we had 50 milliliters, and now we've added 10 milliliters to it. So now we're talking about 0.060 liters. Okay? And so once we calculate that out, so for acetic acid, that's going to give us 0.0667. Hold on, let me redo that. Okay, so 0.0667, and then for our for the acetate ion on its own, we're going to get 0.0167 for molarity. Now, why do we need that? Because we're doing equilibrium, and these bracket guys mean molarity, right? And so now we're at an equilibrium state, and so we're looking for equilibrium, and so we're going to set up our good friend, the ice table. Now, as we talked about in classes, we did some of these. Remember that your basic setup is going to be the same in each case. What's going to happen is you're essentially just changing the numbers here. Now, my ice table is going to look almost exactly like it did before as far as the outer setup. Okay, and this is where, guys, you might want to say, hey, I'm just going to use the generic form of an acid because, Lord, that takes too long to write that. And you would be correct there. Okay, so what are my initial concentrations then? So of my H plus, okay, I've got 0, right? Of my acetate, I've got 0.0167. And then of my acetic acid, I've got 0.0667. So what's the change that's going on? Well, we're still in an acidic situation, so that this still applies. Okay, I'm still producing H plus and losing acetic acid. Now it's pretty easy to tell because that's 0, and I pretty much have to, right? Or I violated some crazy laws of physics and chemistry. So plus X, I'm producing hydrogen. I'm also going to produce some more acetate, and I'm going to lose some acetic acid. So that leaves us with this guy. Now, we could go and plug all of these in to our equilibrium, but in the interest of time, I'm going to do what we all know is going to end up happening here anyway, and that is, I know that since I'm still working with that same Ka of 1.8 times 10 to the negative fifth, that I can probably assume these away. And so I'm going to go ahead and do that when I set up the math here. So 1.8 times 10 to the negative fifth, that equals X times 0.0167 all over 0.0667. And then we're going to do our algebra there. Okay, and I'm going to leave you guys to do the algebra. I'm going to trust that you can handle that. We're going to get 7.19 times 10 to the negative fifth. That is the coolest times 10 you've ever seen in your life. And so again, our X value is our H plus, and so we're going to plug that into pH. Okay, negative log of this guy, and that's going to give us a pH of 4.14. Now, what does that mean for us in the graph? So we hop back to our good friend the graph, and just for the sake of consistency, so we're at 10 milliliters and we're at 4.14. Remember, if this is 7, Halfway here is 3.15, right? And so 4 is probably somewhere around here. Okay, and so we can sort of see the beginnings of our graph starting to take shape, that slow curve up that we're then going to go into our equilibrium curve. Okay, so I'm going to stop there for this part of the video, and then I'm going to pick up again with video part 2 so that you can watch